Hey y'all. Today we're starting to learn about the normal distribution, which you've already kind of seen a little bit of in the past with the empirical rule. We've talked about something being normally distributed, so we're going to get a little bit further into that today. And I'm going to split it up into maybe, I'm thinking 2 lessons. So this is in your notes, chapter 6, if you're following along. And I think that you'll really enjoy it. Okay, so a variable is considered normally distributed if its distribution has the shape of, you guessed it, a normal curve. And a normal curve, we've talked about before, is bell-shaped. So it has this flat, and then it bells up, and then it's flat, and it's symmetric. We've talked about left skewed, right skewed, and symmetric, and we're talking about the symmetric distribution. So to assess whether a variable is normally distributed or not, we can use a normal probability plot. And we will do that, not in this video, but in the next one, you can see what that looks like. The total area under a density curve is equal to 1. So a density curve is kind of another name for a normal curve. A density indicates kind of like a volume or an area, or like you're finding this multi-dimensional type thing. So it's density curve gives you the area, basically. I'm trying to word it differently, but I'll just be frank with you, the area. When you calculate the area under a curve, the number given represents the area to the left of the value. So we're going to look at a table in a couple seconds or a couple minutes, and this table is going to give you these values, and all of these values represent the area to the left. And I'll show you in a picture in a second. If you don't want the area to the left, then we use what's called the complement, which we learned in probability. And the complement is everything except the area to the left. And if the whole area is 1, I'll draw a picture. I'll show you. So we have this normal curve. Mine's a rough sketch. And we'll say we want to find the area to the left of this value, whatever it is. And let's say we don't want to find that. We want to find this. Well, the whole area is 1. And so to find the missing piece, we can do 1 minus this purple stuff, and that will give us the area to the right. So 1 minus the area of the left will give us the area to the right, which is the complement. So if it asks you, it says the area under the curve that lies to the left of 5 is 0.375. So it's saying, if you can picture in your mind this bell curve, and it's saying that the area to the left of this value is 0.375. So I'm just going to kind of sketch it. I don't really know exactly where that is, but I can give you a rough idea. Might sneeze soon. So this area, this is 5, we'll pretend. This area is 0.375. That's what it's telling us. The area under the curve that lies to the left of 5, some value in our distribution, is 0.375. So it says in part A, what percentage of all possible observations of the variable are less than 5? Well, the area is representing the percentage of the observations within that range. So we can say the percentage of observations less than 5 is 0.375 times 100 to move it to percent. We get 37.5%. So we can say 37.5% of our observations are less than 5. And then what percentage of all possible observations of the variable are at least 5? So think about the wording of at least. at least 5 means it can be 5 or bigger, which means that we're talking about this area. If I know that the whole thing is 1, and I know that this piece is 0.375, then how can I use those two values to find the missing piece? You guessed it, subtract. 1 minus 0.375, or you can do, since we're talking about percent, 100% minus 37.5%. Those are really the same thing. In one case, you would get 0.625. In the other case, you get 62.5, and they're the same as long as you convert them to percentages. So 62.5% is at least 5. So that's how they are using areas under a curve. When they say the area under the curve to the left of 5, they're talking about a percent. So if the area under the density curve y equals 2x, that's not really a curve, it's a line, but it's okay, we'll go with it, is x squared for x values between 0 and 1, so they're kind of giving us a domain here. Find the percentage of observations of the variable that are at least a fourth, and then part B in a second. So I'm just going to draw a little sketch of this. It says that my domain is 0 to 1. My scaling's a little off, but it's a sketch. I'm going to draw the line y equals 2x, just to kind of give you a visual of what's happening here. This doesn't really matter to the problem necessarily. We don't really need to draw it, but I just kind of want to show you. And the density under the curve from 0 to 1 is represented by this function x squared. So there's our area, and they're wanting to know the percentage of observations of the variable that are at least a fourth. 2, 3, so here's a fourth, which means they want this area, but we really only know how to find this area. So we're going to first find that by using x squared, since x squared represents the area under the curve. We're going to use that formula to help us find at a fourth what it is. To do that, I squared 1 and I squared 4 and I got 1/16. And then it is asking the area or the percentage that is at least a fourth. So what we found is the area that was less than a fourth, so we're looking for its complement, and we get 15/16. And if I figure that out as a decimal, I get 0.9375. So as a percent, we can say 93.75% of our values are at least a fourth. Then if we want to find the percentage of observations that lie between a half and 3/4, then you're going to find the percentage for a half and the percentage for a 3/4, and you're going to subtract those two. So we're looking for kind of this space right here in the dotted area. My picture's getting messy, but you get my drift. So we do 3/4 squared minus a half squared, and we get 9/16 minus 1/4. I'm going to go ahead and get a common denominator. and we get 5/16. If I divide that, I get 0.3125. So that is 31.25% of our observations lie between 1/2 and 3/4. So not too bad, right? Okay, next page. It is rare that a distribution has the exact shape of a normal curve, so it's okay if something is approximately normal or has an approximately normal distribution. As long as it's pretty close, then you can say it's approximately normal, and then you can use all this stuff. A normal distribution is symmetric, and it is centered about the mean. And the spread of the distribution depends on the standard deviation. So you can kind of see all the things we've been learning are coming together here. So a normal curve has these 3 characteristics. It is bell-shaped, it's centered at the population mean, and it has a range of 3 standard deviations above or below the population mean. So if you were to sketch a normal curve, I've already kind of done a little bit where we have this bell curve. That's terrible. That's a bad picture, but it's just a sketch. We have our population mean in the middle, the center. And then we have 1 standard deviation above, 2 standard deviations, 3 standard deviations, 1 standard deviation below, 2 standard deviations below, 3 standard deviations below. And we learned with the empirical rule, as long as your data is normally distributed, that 99.7% of the data lies within 3 standard deviations, 95% of the data lies within 2, and 68% lies within 1 standard deviation of the mean. And so we're kind of expanding that. They've given us these standard values where 68, 95, and 99.7, and we're extending that to say, well, what if it's not perfectly 2 standard deviations, or what if it's not perfectly 3? What if it's 1.96 or 1.65? Then you can use those values and help you find something that more closely represents your data. For a normally distributed variable, the percentage of observations that lie within a range is equal to the area under its associated normal curve. And a standard normal distribution has a mean of 0 and a standard deviation of 1. So you're going to see this in a second. Just a standardized curve. Whenever you see these in a textbook, you'll have a mean of 0, and then it goes up 1, 2, 3, down 1, 2, 3, and so on. You've probably already actually seen it. And remember, to standardize an observation X, we can use z-scores, and this was the formula. We've already used it for z-scores. X minus the mean divided by standard deviation, and this gives you the number of standard deviations the value is above or below the mean. So we'll use that down here. Properties of a standard normal curve. A standard normal curve has these characteristics. It's bell-shaped. It's centered around 0 with a standard deviation of 1. So the total area under the curve is still 1. The curve extends indefinitely without ever touching the horizontal axis. So you've already seen me draw it up here. You notice it's kind of levitating up there. That's actually part of the characteristics of it. And the curve is centered about 0, and almost all of the area lies between -3 and +3 standard deviations. I've already talked about it again. with the empirical rule, we know that 99.7% of the observations lie within 3 standard deviations of the mean. So to find the area under a standard normal curve, you can use the tables in your textbook or you can use a calculator. I'm going to show you both because it's valuable to understand where these numbers are coming from on your calculator. So I do want you to get comfortable with your calculator because statistics is a lot of technology based. If you go on into other statistics, you might even get into some programming. So I want you to be comfortable with technology, but at the same time, I want you to understand that the values you're getting on your calculator are not just random values and we don't know where they came from. These values are based on these numbers that have, already been calculated, and they can be found using your tables in your textbook. I believe it's in the front in this book. There's a little thing, a little insert. Actually, I ripped mine out in one of my books because I was tired of coming to the front. But if you're renting, don't rip it out. But if you bought your book, you can rip it out. Anyway, it has all the tables on here. You'll see it has Z tables. Where is it? Where is it? I've lost it, but it's in there. So, and I took pictures of it in the notes, so you'll see it. And if you don't have that in your textbook, if someone ripped it out and you rented your book and it's not there anymore, you can just Google Z-tables, and there's tons of images of Z-tables on the internet. So the area given represents the area to the left of the Z-score, and we talked about that on the previous page. So anytime we're talking about area from a table or area that was given from your calculator, we are showing the area to the left of the Z-score. And remember, Z-score on a standard normal curve, that's really bad, but it's actually kind of skewed, but it's okay. It has a mean of 0, and then we have these standard deviations. And your Z-score is, you have an observation X, whatever it is, and you've plugged it into your formula up here, and maybe you found a Z-score of 0.95, I don't know. Then you could find 0.95 is here. You could find the area or the percentage of values that fall below 0.95, a Z-score of 0.95. So that's kind of where we're going. Determine the area under the standard normal curve that lies to the left of 1.25. So if we've got our sketch, oh my goodness, that was horrible. And I'm kind of just eyeballing where 1.25 is. What I'm looking for is the area to the left of 1.25. So my Z-score is 1.25, and the table is giving me the area to the left. So I have this table here. Like I said, you can get a table like this from just a Google search or from your textbook. And you're going to go, you see this little Z right here. So these represent the first digits of your Z-score, and these represent the last digit. So our number is 1.25, so we're gonna go to 1.2 over to 5 right here, and that is 0.8944 right here. Oh, that's ugly. Let's fix it. There we go. So the area to the left of 1.25 is 0.8944. This means that 89.44% of our observations are less than 1.25. a z-score of 1.25. So these values represent area, and these values represent z-score. Isn't that fun? You can also use your calculator, which is nice. Depending on your calculator, this is a TI-84. If you have a TI Nspire, it's a little different. You can use negative infinity here instead. But basically what you're doing is to find the area, we use what's called normal CDF, a normal curve. So you go to second vars, and you can see above second vars is DISTR. It stands for distribution. Isn't that neat? So you go to second vars. Don't turn your calculator on. Second vars, go down. It's number 2 for me, to normal CDF. Hit enter. And you're wanting to tell the calculator that the area you're looking for, if we look at this picture here, this extends into negative infinity, but the TI-84 doesn't have negative infinity in the calculator. So instead of trying to write negative infinity, what you're going to tell the calculator is a really, 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 really small number all the way to 1.25 with a mean of 0 and a standard deviation of 1. So you're going to type in 4 values here. We've got a left bound is what it's called. I put -1. I just made a really long, really big negative number, I guess small in this case. It's really, really small. Left bound. And then this is my right bound. I'm stopping at a z-score of 1.25 with a mean of 0 and a standard deviation of 1. So you're putting in 4 values there. So I'm going to type in negative because it's a left bound, big number, comma. The comma is above the 7, 1.25, comma, mean, comma, standard deviation. Close the parentheses, enter, and we get 0.8944, which if you check with the table, yay, it matches. So that's where that value comes from. It is helping you find the area under the curve with a z-score of 1.25. Okay. Now find the area under the standard normal curve that lies to the right of 0.79. Oops, there you go. So I've already kind of talked about what we have to do if it's to the right, because it's its complement. So I want you to pause it and try it. I did put a table. This is not in your notes. I added this later. You have the table in your textbook if you want to use that. But you're finding the area to the right of 0.79, so the z-score is 0.79, and you're finding the area. So go ahead and pause it and come back and check your answer. Whoops. If you use the table above, you should have found that the area under the curve to the left of 0.79 is 0.78524. So to find the right, we're going to do 1 minus, that got weird, I think because I have it zoomed in too far. Let's try that again. I'm going to go down here. 1 minus 0.78524. You should get about 0.21, I think. 0.78524. Yeah. We get 0.21476. You don't have to go that many decimal places. You go to 2 or 3 decimal places would be fine. So about 21% lies to the right. So I want to show you a picture of that because you might get caught up in the wording. we're saying the z-score is 0.79. And the table gives us the area to the left. So what the problem is asking for is not this. It says, what's the area to the right? So sometimes it can help if you draw that picture to give you that visual of, what am I finding? These values give you the area to the left. So if you draw a picture, you can see, oh, okay, that's that area, but they want to the right. Well, if the whole thing is 1, then to find the right, you do 1 minus the 0.785, and you get about 0.21. Or if you chose to use your calculator, which is fine, your left bound is 0.79. Your right bound is a really, really big number. You can go bigger than that if you want. And then your mean is 0, your standard deviation is 1, and that will give you the exact value you need. You won't have to do any subtracting there because you're telling the calculator that you want this side by saying, this is my left bound, this is my right bound, which kind of signifies infinity. If you're using a TI Inspire, then you can just do infinity. And then mean standard deviation. So if you use your calculator, you don't have to do any subtracting. You can just type it in like that and it'll give you the correct answer. If you're using the table, then yes, you do have to take into consideration the subtraction. So be careful about that. I know it can be confusing. I would recommend maybe picking one method and using it every time so you don't get confused in your mind. Although I will say, when you draw the picture every time, you'll start to realize what you're finding. I don't want you to just find the values to finish the problem. I want you to find the values and understand what they mean and where they're coming from. So the next one, it says find the area under the standard normal curve that lie between z-scores of negative 0.67 and 1.25. And this is not in your notes, I added it later. This is a negative z-table. Again, it's in your textbook, so if you have the tables from your textbook, you can use that. If not, there's that, I added it in. Remember, when we're finding the area between two values, we find the area of each one and subtract. So go ahead and try it and come back. Okay, so if you use the table, we had actually already found the area for I keep saying that, 1.25 above, that was 0.8944. And if you use the table for negative 0.67, you get 0.25143. So then you subtract those areas minus 0.25143, and we get about 0.643. So 64.3% of the values lie between those z-scores. And then if you chose to use your calculator, then you would type in, see if I can make this work, normal CDF. Your left bound is negative 0.67. Your right bound is 1.25. Mean of 0, standard deviation of 1. Close your parentheses. And if you type that in, you will get 0.643. Whoops. Oh no. Here we go. Sorry. Take you on a wild adventure. 0.643. So 64.3% of our observations lie between negative 0.67 and 1.25. Isn't that neat? Isn't that so fun? Okay, next page. I've already talked about this. What do the areas represent? They represent area represents the probability which is actually probability, which is the expressed as a percent, that an observation lies within a certain range. So if you're solving for a variable, we're going to use this and move into something else. If you were solving for a variable and you wanted to undo something or work backwards, we actually call that an inverse operation. When you do the opposite of something, you're using the inverse. So if you're adding something and you want to subtract it to undo it, that's called an inverse operation. In the tables, in the previous problems, we were given the z-score, and we used the z-score to find what were these? Area. So if we're given the area, then we can look in here for that area to find the associated z-score. So it says, if the area is 0.5910, what is the z-score? So we're kind of working backwards. So we go in here and we look for 0.5910. I'm going to circle it. 0.5910. And it is associated with 0.23. Whoops. So remember the left side, that's your first digits. And then when you go up, that's your next digit. So the z value associated with that area is 0.23. And if we look in the calculator, obviously we can do this in the calculator. So if you look in the calculator and you go to second vars, which function, if we've been using the normal CDF, which function do you think would allow us to work backwards? So these are your options. And I've already told you a little bit, if we want to go backwards or find the opposite, we use the inverse, right? So in the functions, which one looks like it might be an inverse? Inverse norm. So inverse norm is going to help you find, if given the area, it's going to help you find the z-score. And that's number 3 on my calculator. So use your calculator to confirm that we got the correct z-score from the table. So you'll type in inverse norm. Well, you won't type that in. You'll grab that from the function menu of 0.5910. 0.5910, close it, and we get about 0.23. Yay! That means we did it correctly. So when you're given the area and you want to find the z-score, we use inverse norm. And that's here. Oh, I didn't put in my calculator, I didn't put in the population mean and standard deviation. I think they just assume that that's what you mean, unless otherwise stated. Yeah, I got the same thing. So I typed this in. Down here, I'm saying to type in the area, the mean, and the standard deviation, but you get the same thing, so it's okay. Okay, last page. Okay, the last thing we're going to look at, hopefully I don't confuse you here. The symbol Z sub alpha or Z alpha is used to denote the z-score with an area to the right of alpha, which is like, wait, what? I thought we were talking about the area to the left. Now why are we talking about the area to the right? What does that mean? Well, these values are leading into something that we'll talk about later called critical values. And these values are important for finding the probability of, or seeing if something is unlikely. It's a long story. We will cover it later. But basically, alpha is talking about the area in the tails. So this is a standard normal curve. This isn't in your notes, so you might want to draw it in if you want to. I added this in later. And alpha represents the area to the right because it's talking about the area in these tails. And these tails are representing a very small percentage. So this relates later on when we get into like hypothesis testing and stuff and p-values and critical values and stuff like that. And basically we're finding this area, if something is in this area, then it's like really unlikely to happen, because this represents, you know, maybe 99.7% of the data. And so if something is in here, then that's a really small percentage of happening. So Z sub alpha is representing this area in the tail. And we use that, we kind of have to work around it a little bit because our tables give us the area to the left. So if Z sub alpha is telling us alpha is the area to the right, then we have to kind of use its complement since our tables are to the left. So you'll get it, don't worry. Our areas in the tables and calculators represents the area to the left, so we have to do 1 minus alpha to help us relate the two. So obtain the z-score that has an area of 0.95 to the right. Let's just draw that. Oh my. So an area of 0.95, that's a lot, to the right. So we're finding the z-value that represents this area of 0.95, which means if we're going to be using our tables, I need this, and that is 0.05. So I can do inverse norm to find the z-score with an area of 0.05, mean of 0, standard deviation of 1. So go ahead, you can use your table too. You could find 0.05 in the area portion of the table, and then find the associated z-score. In your calculator, you can do inverse norm 0.05, comma 0, comma 1, parentheses, and we get about negative 1.645. So this z-score is negative 1.645. Okay, try to find example 5. It is actually already asking you, just draw a picture. Just try it. See if you can figure it out. Okay, if you drew a picture, that really helps because it shows you what you're finding. It's saying that the area to its left of the z-score is 0.75. So in order to use my table or my calculator, I don't actually have to end up subtracting anything because to the left is what I want. So I can go ahead and either look at my table and locate 0.75, or I can do inverse norm of 0.7501. And we should get about 0.678 is the z-score, I should say. The z-score associated with an area of 0.75. So the z-score that has 75% of the data below it is 0.675. The z-score that has 95% above it is negative 1.645. Isn't that so neat? Okay, so down here we have it in the z sub alpha form. Remember that alpha represents the area to the right. It's this little tiny tail. So if we're wanting to find the z-score with this little tiny tail where the area represents 0.04, if I'm looking for this z-score, I actually need this area in order to figure out my z-score with inverse norm or the table. So that's going to be 1 minus alpha, which is 0.96. So I'm going to do inverse norm of 0.96. And if you want, pause it and try to find that. You should get 1.75, which makes sense because it's over here in the positive. So you can see here when the 0.95 was to the right, we ended up with a negative z-score, which makes sense because it's less than the mean. And then over here, we ended up with a positive z-score, which means that it's greater than the mean, so it kind of makes sense with our picture. That's why I like drawing a picture. Okay, pause it and try to find B and come back and check your answer. So you should get about a z-score of 2.576. So this 0.005 puts it way over here with a teeny tiny tail, which a z-score of 2.576 indicates 2.576 standard deviations above the mean. So that's over here. And that's kind of a lot. Not unusual, because remember, if it's above 3 standard deviations, then it's unusual. So it's not unusual, but it is above 99.5% of the observations. So that's definitely going to play into percentiles. If you've ever heard of percentiles, then you kind of see how this might be relating. This z-score is above 75% of the rest of the observations. This z-score is below 95% of the rest of the population, or observations. This z-score is above 99.5%, so you can kind of see where that's going to come in later. But that's all I have for this lesson. I hope you enjoyed it. If you have any questions, please let me know, and I would be happy to help.